prior to going on and watching this. Okay, with that said, symmetry. I want to talk a little bit about symmetry here. Okay, so symmetry is an interesting concept, and it ends up leading to some rather interesting behavior in functions. And so what we do is we classify functions based upon many times by their symmetry. So let's take a look at a couple of our toolkit functions here. Our pal f of x equals x squared, and the parabola, and f of x equals the absolute value of x. And when we notice that both of those, that if you reflect those about the y-axis, you get the original graph back. In other words, if I took f of x and I said, well, hey, here's f of x equals x squared. If I reflect that across the y-axis here, notice that I'm going to end up back with the same graphs that I began with. Same thing with the absolute value of x. Okay, so graphs that exhibit this type of behavior, we say are symmetric about the y-axis. In other words, if I took a mirror and I laid it down on edge on the y-axis, what I would see on one side of the mirror would be the same as I saw on the other side of the mirror, assuming, of course, it's a two-sided mirror. Okay, so keep that in mind. So that's the first type of symmetry we're going to talk about, symmetric about the y-axis. Okay, now similarly, the function f of x equals x cubed, that also exhibits a type of symmetry also. In this case, it's not only reflected across the x-axis, but also across the y-axis. So if I take with my stock function here, f of x equals x cubed, and I reflect that across the x-axis, excuse me, the y-axis, my pardon. And so in other words, I take this point and I move it over to here, and I take this point and I move it over to here, and I take this point and I move it over to there, and I take this point and I move it over to there. Then notice I end up with f of negative x. In other words, that's reflected across the y-axis here. Okay. Now, if I take this function and I flip it again, excuse me, but this time I reflect it across the x-axis. In other words, I take this point and move it down here, take that point and move it up there, and lo and behold, I end up with this one. So notice the interesting behavior here is that f of x, our original function, happens to also be equal to the opposite of f of negative x. In other words, if I reflect it across both axes, I end up back with the original function. Let's go back up and write what we talked about in the previous slide with symmetric to the y-axis. Let's talk about that symbolically also. Notice that here, if this was my original f of x equal to the absolute value of x, well, it's also equal to the opposite of x in absolute value. And likewise here, if I have f of x is equal to x squared, that's also equal to the opposite of x quantity squared. So what that tells me, symbolically, is that f of x is equal to f of negative x. In other words, those two functions will be graphed exactly the same. Okay, so time to get out your comp books. I'm going to go through this quickly, but I just want to remind you, you need to get this in your reference book. We give names to both of these. We say that if the case happens where f of x is equal to f of negative x, in other words, if it's symmetric about the vertical axis or the y-axis, then we say that that function is an even function. Likewise, if we say that f of x is equal to a graph that's been reflected across the y and the x-axis both, in other words, the vertical axis and the horizontal axis, by the way, we call that type of symmetry symmetric to the origin, then we say that that is an odd function. Okay, let's go explore this just a wee bit in Desmos to see why that is what it is. Okay, so let's take a look here. Let me adjust my Desmos window just a tad for you here because I have it off screen just a bit, but I can fix that if you give me just a second here. All right, maybe more than a second. Yes, to the best laid plans, right? Okay, so let's shrink up this window quite a bit here because I had it a little bit too big for the video's sake. Okay, there we go. All right, so here's f of x equals x squared. Well, let's go up here and let's change that squared. Let's make that a parameter. Let's make it a, okay? And I'm going to add a slider for a here. And I'm going to have a go from, we'll stay with just positives for a minute. We'll have a go from 0 to, let's say, oh, I don't know, let's say 10, and we're going to go in steps of 1, so it'll only move by 1 for me, okay? So now, when a is 1, we got f of x is equal to x, which that's our old pal, the identity function. We know that one. That's one of our toolkit functions, right? So if I bump a to 2, then notice we get the parabola. I bump the a to 3, and we get the cubic. I bump a to 4 and we get something that looks like a parabola. I bump a to 5, we get something that looks like a cubic. I bump a to 6, I get something that looks like a parabola. I bump a to 7, I get something that looks like a cubic. Obviously they're different, but they exhibit similar behavior to both the cubic and the square, okay, the parabola and the cubic, all right? So that's where the names odd and even get. Let's go through it one more time. See, odd number, even number, odd number, even number, odd number, even number. Symmetric to the origin, symmetric to the y-axis. Symmetric to the origin, symmetric to the y-axis. Are you getting it? So when it's even, it's going to be symmetric to the y-axis. When it's odd, it's going to be symmetric to the origin. So that's where we get those fun names, odd and even there. Okay, let's go back to the regularly scheduled program here, okay? Alrighty, so let's take a peek at a couple problems here. It says for each of the following equations, determine for these functions whether the function is odd, even, or neither. Okay, so what you're trying to determine is it symmetric to the y-axis or is it symmetric to the origin? Okay, now there's a couple of different ways of doing that. My first suggestion would be, let's go back to Desmos real quick and let's graph it, and let's do it from a graphical standpoint. In other words, let's see if it's odd or even based upon its graph. That's really one of the easiest ways of doing it, okay? So let's see again. What was our first function here? Let's get back to where we need to be. That was x minus 2 quantity squared, okay? So x minus 2 quantity squared, and no, well, it does exhibit symmetry. It's not symmetric to the origin. It's symmetric to the line y equals 2. And excuse me, to the y-axis, not to the origin. It needs to be symmetric to the y-axis in order for it to be an even function. So that is not an even function. Okay, so that's how we would check it from a graphical standpoint. How would we check that algebraically? Well, in order for it to be an even function, what has to be true is that f of x has to be equal to f of negative x. So let's try that. Let's go plug in negative x and see if we get back our original function. In other words, let's take f of negative x and let's evaluate that. And what we see is we end up with negative, whoops, sorry about that, back up just a few steps here, negative x minus 2 quantity squared, which is not equal, that is not the same function as x minus 2 quantity squared. So therefore, it exhibits none of them. It is neither here is what you would say. Okay, what about g of x is equal to 2x to the fourth? Well, I'm going to let you do the graphical part here on your own. What you should see is that is symmetric to the y-axis, okay? So let's let's take a look at that from an algebraic standpoint. In other words, let's take a look and see what is f of negative x. And our question is, what we're trying to answer, is that the same as f of x? So let's give it a go, okay? Actually, how about we put f's in there instead of g's? That would be a good idea. Let's just get rid of all that. There we go. So is g of negative x equal to g of x? Okay, so with that's the question of the day here. It says plug in a negative x wherever you find an x, so that it'd be 2 parentheses negative x raised to the 4th power. And if I take negative x and I raise that to the 4th power, I get back x to the 4th. And so frapulous joy, this one indeed is symmetric to the y-axis or symmetric to the vertical axis. Therefore, it is an even function. Okay, so just by, process of elimination, I'll bet you that h of x is odd, but we're going to go through it anyway because you need to be able to show it, okay? So again, I'm going to invite you to do the Desmos part. I'm not going to do this part for the graph for you, but graph this and take a look. Does it exhibit symmetry about the origin? Well, how do we tell that from an algebraic standpoint? Well, the question now is, remember, we're reflecting across both axes. So if we're going to reflect across both axes, we want to know is if I reflect across the x and I reflect across the y, is that going to give me back my original function? Okay, in other words, do we get the same function back again? So let's give that a go. So let's see. So it's the opposite of h of negative x. It's a little tricky to do here. We've got to kind of go a little slow. So that's going to be the opposite of parentheses because it's the whole thing, right? And then now I got to change the inside part too. So that's 2 negative x minus negative x cubed. Okay. All right, let's take care of the inside first. Working from the inside first, let's see it's going to be opposite of negative 2x, because 2 times negative x is negative 2x. And then this is going to be what? Negative x cubed. Negative x cubed is going to be a negative and a negative, right? Because if you use cube and negative, you'll get a negative x cubed back, right? Which is going to give me the opposite of negative 2x plus x cubed, right? And then I distribute that negative and I get back 2x minus x cubed. Okay, so was that our original function, or did we come back to the original function? Did we come back to h of x? And the answer is yes, we did. Okay, so this, since it passes the test of being symmetric to the origin, would be an odd function. Okay, you'll find that odd and even functions show up in lots of different places. The trigonometry is full of them, and so is calculus. So make sure that those definitions make sense to you, and work as many problems as you need to tell how I just did it by doing the substitution works. Okay. All right, let's switch topics here. So another type of translation or transformation that we can make of a function is a stretch or a compression. It's basically a scaling factor. So we're going to change the shape of it slightly now. We're either going to compress it or we're going to stretch it. So these are non-rigid transformations. In other words, the graph is going to look a little bit different than it did when we put these particular transformations on them. Now, the previous transformations, other than the reflections, those were additive. In other words, when we did a shift, when we shifted the function either horizontally or vertically, then that was additive. In other words, we added or we subtracted something. So in the case that we just saw with reflections, so when we did a reflection, that was multiplicative. In other words, we multiplied by a negative 1. Okay, so now we're going to up the game here, and it's not going to be limited to multiplying by a negative 1. When we do a stretch, when we do a compression, that means we're going to multiply by a value. So you're going to multiply, generally speaking, we're going to look at numbers that are between 0 and 1. Some scaling factor, we'll say call it A, or some number that is greater than 1. Those typically is how we're going to break it up. It changes depending upon whether the number resides between 0, 1, or greater than 1 as to whether it's going to be a stretch or a compression. So let's get into this and see if we can actually breathe some life into this conversation, okay? All right. So vertical stretch or compression and a horizontal stretch or compression. We'll start off with that. Be sure that you get that into your comp book, okay? You're going to need this as reference. Make sure that this is someplace where you can get to it easily. I invite you, in fact, I think it's a really good idea that you keep this with you and use it when you're working on the homework here, okay? All right. So let's talk a little bit about what is going on here, and then we'll go to an example in Desmos, okay? So this is a really good introductory example. This is right out of the book, okay? And it says create a table for the function g of x equals f of 1/2 x, where f of x is given by this. So this is our function f of x, okay? And they want us to create a table of f of 1/2 x. Okay, so the formula for g of x tells us that the output values of g are the same as the output values of the function f for an input half the size. So notice that we don't have enough information, for example, to get g of 2. So if we went over here and tried to do g of 2 using this table, well, we're kind of hosed, because g of 2, well, you'd plug it in there. That's half of whatever the input is into f, which would give us f of 1, and there's nothing in the table that tells us what f of 1 is. In other words, we don't have f of 1, so we don't have an output for it, right? So our input values of g need to be twice as large to get the inputs for f that we can evaluate. For example, if we determine g of 4 equals f of 1/2 times 4, which is equal to f of 2, and that's equal to 1. And so similarly, g of 8 would be equal to what? Well, that's f of 1/2 times 8, because notice that's my x value, right? which is equal to what? Well, that's equal to f of 4. And back up here in this table, we notice that f of 4 is defined. F of 4 is equal to 3. Okay, let's go put those points onto Desmos. Okay, so let's go and get into Desmos here real quick. Let's go graph these. I'm pretty sure I saved this. I did. There we go. All right, so let's open this graph. Let's shut off all these crazy guys right here because we don't need to be seeing those at the moment. Okay, so here are the points that we just looked at. Okay, so here's the table for F. I don't know why there is a 10 in there. Shouldn't be. Here's the table for F, and here's the table for G. Okay, in other words, the X1s were the original table, so that was my F's. Okay, and then here's the function G. All right, so in the function G, what you notice, what's going on, is that these values are getting pulled over to the right by 2 units. This is what we refer to as a horizontal stretch of the function. It's getting moved off by 2 units to the right-hand side of it. Okay, so a horizontal stretch is a more difficult beast to deal with. It is why we're starting with that one first, because it turns out the vertical ones are a lot easier. But we're going to concentrate on the horizontal one for just a moment, try and make sure that makes sense, and then we'll go back and talk about the horizontal ones, I mean the vertical ones. So the horizontal stretch here was by 2 units. Okay, so let's go back up and take a look at our table here for a moment. So horizontal stretch is a compression. So given f of x, we define a new function g of x, where g of x is equal to f of bx, where b is a constant, and g of x is a horizontal stretch or compression of the function f of x. If b is greater than 1, then the graph will be compressed by 1 over b. If b is between 0 and 1, then the graph will be stretched by 1 over b. If b is less than 0, then not only are we going to have a horizontal stretch, we're also going to have a horizontal reflection. But we'll deal with those separately. We'll take these on as in different pieces. Okay. So let's do a quick moment here. I'm going to pause the video for a moment because I just realized I need to add a blank slide. So I'll be right back with you. You guys just hang tough. I'm going to pause my recording here for just a second. Okay, so back. Sorry about that. I had to put a blank slide in real quick because I left myself not enough room to do this. Okay, let's go talk for a moment about vertical stretches and compressions. And we'll come back and we're going to combine the two ideas together. So far what we have, just to recap here, we've got horizontal stretch and compressions. And if you're feeling a little lost at the moment, you are in good company. Just hang tough. This is going to make way more sense when we actually start working some problems. But we need to till the ground to make it so that those seeds that we plant are going to make sense to you. Okay, so horizontal stretch or compression, what we know so far is that if you have a horizontal stretch or compression where, let's scroll back up to the box here for just a moment. There we go, where we're looking at g of x is equal to f of bx, where b is the constant. If b is greater than 1, then it is compressed by 1 over b. Okay, so b greater than 1, then we're compressed by 1 over b. Okay, similarly then, that would say that if 0 is less than b, which is less than 1, then we are going to be stretched by 1 over b. Now just hang on to that. Keep that in your hip pocket. We're going to pull it back out here in just a minute when we start using it, but we need to have that information at our fingertips. Okay, so that's the horizontal stretches and compressions. Let's do the easier one now. The easier one is the verticals. So a vertical stretch or compression. Okay, so if I was going to do a vertical stretch or compression, let's go back into Desmos here real quick. So let's take a look at a new graph. Okay, so let's take a look at our old pal, f of x equals x squared. Okay, I got a better idea. Let's use square root. I think let's just change it up a little bit. Do something a little more gnarly. Let's do square root of x. Okay, so there's our pal square root of x, okay? Now, notice that if I come in here and I say g of x is equal to, get rid of my keyboard here, 2 times the square root of x. Okay, I'm not going to get rid of the keyboard because I won't. If I go 2 times the square root of x, notice that what happened is that graph got pulled up towards the y-axis, didn't it? So it got stretched vertically, is one way of thinking about that, okay? Similarly, if I said h of x is equal to 1/2 the square root of x, notice that that got pushed down. In other words, it got squished. That got compressed vertically. And so that's one of the key ideas with the names, with stretch and compression. Excuse me, when you stretch something, that means you're pulling it towards that axis. When you're compressing it, it means that you're pushing it away from that axis. The reality of the situation is that I can turn both of these into horizontal stretch and compressions also. So if I bring that 2 inside of g of x, okay, and I say, okay, let's call it k of x is equal to the square root of 4x. Notice it plotted right over the top of g of x, didn't it? The k of x and g of x are right on top of each other. Let me clear off both these other two functions to prove that to you. See, those two are just graphed right on top of each other. And similarly, I can do the same thing with h of x, okay? So I can say, well, you know what? J of x is equal to, let's turn this one on and shut these back off, okay? It's the same thing as the square root of 1 divided by 4 of x, okay? Notice they plotted right on top of each other. The green one and that one did. All right, so it's going to take a while for this stuff to settle in, but be patient with yourself. The main idea is that when you pull something towards an axis, then you are stretching it in terms of that axis. When you're pushing it away from it, then you are compressing it with respect to that axis, okay? And if you can keep that part straight in your head, then the rest of this hopefully is going to make a huge amount of sense. Okay, let's go back to the problems here, okay? So a vertical stretch or compression. So if you are given g of x is equal to a times f of x, then the number out front is going to stretch or compress it with respect to the y-axis. So this is, again, the vertical is respect to the y-axis. This is respect to the x-axis, okay? All right, so if a was greater than 1, then that's going to be a stretch. It's going to pull it up towards the y-axis. If a was between 0 and 1, then that's going to be a compression. It's going to push it down towards the x-axis and push it away from the y-axis. Okay, all right, let's go take this to the road. Let's go see if we can play with the sum and see if we can make it make any sense whatsoever, okay? All right, so write a formula for a function that results from the given toolkit function is transformed as below. So this is number 52. We're back onto the your turn. So f of x, time out, wrong one. I skipped some problems. Back up, Mike. Go do these first. We'll get to that one in just a moment. So 42. Describe each of the function is transformed of the original function f of x. In other words, what happened? What will it do? So these are all new g of x's, let's say. What will g of x look like with respect to the original function? So again, we need words here. That's the only thing we're going to answer with, not graphs or anything. So let's see. We've talked about reflecting now. So we know that if we change the x, in other words, if my x is right here, and then I plot negative x, which is over here, that means I reflected about the y-axis. So this would have been a reflection about the y-axis. Okay, all right, so stop for a moment, write it down before I answer for you. Tell me, what would this one be? Would that be a compression or a stretch, and would it be a compression or a stretch with respect to y, or would it be a compression or a stretch with respect to x? Key way of thinking about it is, again, the 6 is touching the y, it's not touching the x. Okay, cool, so you got it, right? What is it? Okay, so this is going to be a stretch about the y-axis or the vertical axis. I'm going to go x and y-axis. You can do vertical like they do in the book, and that's just fine. And the factor is 6. Okay, what about this one? So are we stretched or compressed about the y-axis or the x-axis? Which one is it? Okay, hopefully you guessed that it was about the x-axis. So is it a stretch or is it a compression? Go look at the little blue box up there that I told you to look at. Remember, you need to have that handy. That's going to really help you a lot. Okay, so this one hopefully you saw based upon the blue box was a compression. It's a compression about what? The x-axis. And it's by a factor of what? Well, it's 1 over b. So it's the inverse or the reciprocal of whatever that number is. So it's by a factor of 1/2. Okay, similarly, is this a stretch or a compression? And if so, about which axis? Well, I'm touching x. So that must be about the x-axis. And this is a stretch. Yeah. A stretch, that would be better, okay? And it's a stretch about what? About the x-axis. And by what now? Okay, so again, you're going to form, when it's respect to the x-axis, you form the reciprocal of the scaling factor. So the scaling factor in this case is 5. All right, last but not least on 50 here, okay? Well, where is that negative? Now we're changing the y values, aren't we? So if you had a positive y value, we're making it negative. So that negative is a reflection across the x-axis. So first thing is that we've got a reflection here. So that's across the x-axis. And what else do you know? Well, it's got a scaling factor, right? So it looks like it's got a compression. And it's a compression about the x-axis. And the factor is 1/3. Okay, so go back and look in the book, and there's odd problems that correspond with 42, 44, 46, 48, and particularly 43, 45, etc. up to 51. Make sure you can do all of those, all right? At least read them and check them in the back of the book and make sure that you got those dialed, all right? Okay, let's move forward into the next your turn here. So write a formula for the function that results from the given toolkit function if it's transformed as described. Okay, so to give us the transformation in English, in other words, this is a reverse from the previous problems we just did, and now they want us to write the new function. They want to know what g of x is. So g of x is some transformation of f of x. So it's reflected across the x-axis. So that tells you that the point was up here, now it's down here. So what that did is that takes the opposite of whatever the original function was, right? So that's the opposite of f, and now it's got a horizontally stretched by a factor of 2. So that's stretched with respect to the x-axis, okay? So if the factor is 2, right, then you've got to form the reciprocal of that. So it's going to look like 1/2 of x. That's the sticky part when you get a horizontal one. Remember that whatever the factor is, you gotta have to use the reciprocal of that. In other words, if you came in here and said g of x was equal to negative f of 2x, I'm gonna cry blood. It's like, no, that's wrong, okay? I know, and it's a little tough. That's why I said it is super important while you're working these problems. Have these out in front of you and use them as your reference to understand what you're doing, okay? And the more of these you make, the easier it's going to get. And when we start graphing some of these in Desmos in a few minutes, hopefully it'll make even more sense. Okay, so let's go ahead and finish it off because they don't want it in this function notation. This, by the way, was wrong, okay? They want it written out as the actual definition. So that's the opposite of the square root of 1/2 of x, okay? All right, let's do another one. says write the formula for the function that results from the given toolkit function is transformed as described. F of x equals x squared is horizontally stretched by a factor of 3, then shifted left 4 units and down 4 units. Okay, now keep in mind the order of operations. So the order of operations tells us that we do multiplication and division, and then when those are done, and only then, we do addition and subtraction. So notice that stretching horizontally or vertically, compressing horizontally or vertically are all done by factors, which means those are multiplication and division. So those need to happen first, and then once I finish that, then I will insert my shift left, right, up, down. Okay? Okay, so let's go see if we can create g of x here. So it's got a horizontal stretch by a factor of 3. Okay, so it's the factor of 3. Since it's a horizontal one, that means I got to take that scaling factor and use the reciprocal of it. So let's not shift it first. So we're just going to do the stretch or the compression first. You want to get in the habit of this. Do the stretch or compression first, and then do the shift. So I'm going to do this in 2 pieces. So if we do the stretch or compression first, then we know g of x is going to be equal to what? Well, it was horizontal, so that means it's got to be next to the axis or the x value. So that's 1/3 of x quantity squared. So now that's not the whole function, because now once I've done that, then I do the shift second. So a wanna and a tua. That's the wanna and that's a tua. You do the stretch or compression, the reflection, all the multiplicative stuff that has factors involved in it first, then you do the shift. Okay, so we're going to have one last function, h of x here. So what's h of x going to be equal to? Well, it's shifted to the left by 4 units. So that means that that's going to be 1/3 to the left by 4 units is going to be equal to what? X plus 4. That's how you shift it to the left. And then once we finish that, we're going to shift it down by 3 units, so that's going to be a -3. And if you do it in that order and keep mindful about what you're doing, hopefully it'll all start to make sense. So what that tells me is that h of x is equal to what? H of x is equal to f of 1/3 times x plus 4 minus 3. In other words, the input into the f function to get the h function was 1/3 of x plus 4. Notice I did that in 2 pieces. I got the third x, then I substituted in the x plus 4 for the x. Go slow, take your time, do whatever it takes, big cup of coffee to make this make sense for you, and it'll go. It will happen, I promise. Okay? All right, number 66. Sticking on the your turn here, all right? So describe how this formula was a transformation of a toolkit function, then sketch the graph of the transformation. Okay, so our toolkit function was f of x equals the cube root of x here. All right, so what happened here? Well, they did some sort of a shift, and they also did some sort of a reflection. So how are we going to figure that out? Well, remember that the reflections are multiplicative. So they multiplied through the reflection. In other words, they multiplied through the -1. So we're going to factor that back out. We factor back out the -1, we end up with x plus 6. Okay, so what this tells me is that this function was reflected. So let's see, the x's got changed. Let's think about that again, so if you forget. So the x's got changed. So the x's were positive and they came negative. Oh, I went across the y-axis. So reflected across the y-axis. And then what else happened? It was shifted 6 units to which direction? Don't say it at once now. Okay, now we need to go check that. So let's go back over into Desmos here. Let's clear out all this craziness from our previous work. And let's go ahead and put in, this is my G, isn't it? What was this thing again? It's a B of x, there we go. b of x is equal to, let's go get my cube rooter here. Oops, that's not what I wanted yet. Never mind. Back that off. Let's go get the nth root. It's hiding over here in miscellaneous. Okay, so this is the cube root of what? Well, we said it was the opposite of, if we go back, we can write it either way. It's negative x minus 6 if you want to do it that way. There we go. Okay, so let's see. So it got reflected across the axes and then shifted. Let's put the other one in. You guys may not be as savvy about seeing the cube root in your head yet as you are with the other functions. So maybe not a bad idea to put the cube root on there with it just so you can see what actually happened there. So let's do that. So there's the original function f of x, okay? So what happened? Well, it got reflected across the x-axis. Do you see that? So the first move, the first thing that happened is it got reflected, right? And then after it got reflected, it got shifted which way? Well, it got shifted 6 units to the left, okay? Now, if you had just said that minus 6, you would have thought maybe it got shifted 6 units to the right. That's why we factored that negative 1 out of there. In other words, that's why we wrote it actually to look like this, to make it so that it plotted correctly. Okay, let's keep it going. The more of these do, the better it gets. Okay, now they're going to give us a transformed graph and they want us to come up with the function of the transformed graph. So it's obviously not only been shifted, it's also had some sort of a scaling factor. Finding the scaling factor can be a little bit of a bugger, but here's a really good trick to help you with it. It helps find the scaling factor. There's always an origin point based upon our toolkit function, and we know that the origin point, or the original point that went through the origin, is right here. It's the bottom of the V. It's the pointy point on the V, right? So what we're going to do is pretend for a moment. We'll call this y prime, x prime. We'll call these a translated set of axes, okay? And from there, we're going to go ahead and look at some points. We're going to go over 1, 2, 3, and up 1. So an x prime, y prime, in other words, an ordered pair in my translated coordinate system here would have been what? If I went over 3, up 1. Whereas 3, 1 is on this function if it was still sitting at the origin. In other words, it had been scaled but not shifted yet. So think about that for a moment in terms of what we've talked about earlier. Is I need to deal with the multiplicative part first. So I'm looking for the scaling factor first. Then once I've got that, then the shift is going to be easy. I just need to know what that scaling factor is, okay? So if we think about in y prime world that this is my function y prime is equal to absolute value of x prime. In other words, that's this graph right here, but there's some scaling factor here. Let's call it an a out front, okay, that squished that thing. I can find that by now plugging in this ordered pair, and I'll be able to figure out what a is. So in other words, in my x prime, y prime coordinate system, notice I went over 1, 2, 3, and up 1. So this ordered pair right here would be 3, 1 in x prime, y prime in the shifted coordinate system, okay? All right, now why is that useful? Well, because I can take that ordered pair and I can plug it over here. I can say, well, 1 is equal to a times what? The absolute value of 3. In other words, plug the ordered pair in, and I see that 1/3 is equal to a. So that tells me that my scaling factor is equal to 1/3. Yes, no, maybe. Hopefully that's making some sense, okay? All right, so since my scaling factor is equal to 1/3, then that tells me that I'm almost home here, because that tells me now that I've got some function f of x that's equal to, well, what? It's 1/3 times the absolute value of x. All right, cool beans, except for that's not my function, because that's my function in y prime or x prime y prime, but I'm not in x prime y prime, I'm in x y, so I need to shift this thing. So how am I going to shift it? Well, it's shifted 2 units to the right and 1 unit up. So my newfound friend here, the shifted one, the answer to this is going to be 1/3 times the absolute value of x minus 2, and then what? Plus 1. Okay, now don't trust me that I got it right. What we're going to do is we're going to go back over into Desmos here real quick, and we're going to graph it and see whether or not that actually turns out to be true. So g of x is equal to 1 divided by 3 absolute, oops, my bad. Get out of that fraction first. Absolute value of x minus 2, close off the absolute value, and then add 1 to it. And bada bing, bada boom, there it is. 1, 2, 3, up 1. Yep, that's the same graph. Okay. So when you get done with your formula, you're going to come back into Desmos, you're going to plot it, and you're going to see whether or not you got the graph right or not. Okay. All right, let's do another one. Okay, write an equation for the transform toolkit function. Okay, same song, second verse. Come in here. Here is my x prime, y prime. Here's my translated coordinate system, that x prime, that y prime, okay? So from here, I noticed that I went over 1, 2, and up 1, 2. So this ordered pair right here in x prime, y prime is at 2, 2. Okay, so why do I need that? Because I know that y prime is equal to a times x prime quantity squared. That's parentheses, those aren't absolute values, okay? So in other words, I know there's some scaling factor that squished or compressed or stretched my particular function. Okay, so let's go see if we can figure out what that value is. We're going to put in 2 is equal to a times 2 squared, which says that 2 is equal to a times 4, which says that what? 2 over 4 is equal to a, which is my scaling factor. My scaling factor is equal to 1/2. All right. Cool beans. Okay, so that tells me in terms of x prime, y prime, that f of x prime is equal to what? Well, it's equal to 1/2 x prime squared, okay? All right, whew. So let's see if we can get this thing into a g of x. So we got to shift it, okay? So it's got to be shifted. My bad, excuse me, there's a mistake here. Let me back up for just a moment. It's 1/2 times x prime squared. There we go. Now I got it. Okay, so now I got to get my g of x here. In other words, I need to shift this thing. Well, it looks like I got shifted 1 unit to the right and 2 units down. So that means it's going to be equal to 1/2 times x minus 1. There's my shift to the right, quantity squared, and then down 2. All right, again, we're going to go check that in Desmos. So we'll come in here, and we'll go in 1 divided by 2, and then you're going to put in parentheses x minus 1, and then you're going to go ahead and you're going to close that parentheses, and you're going to square it, and then you are going to shift it down by 2. And that's looking an awful lot like the picture that was in the textbook, okay? If the picture does not come out the same, then play with it here in Desmos and see what you needed to do to tweak it so you get it to look like the graph in the book. That's not a bad way of doing it, all right? Okay. More of these we do, the happier they get. All right, one more with a toolkit function. This time is going to be with a cube root. So they want us to transform this, and so what do we see? Okay, so it looks like my origin point got moved over here now. All right, so there is my x prime, y prime axes. Those are my new translated axes, okay? And let's see, it looks like if I went over 1 and went up 1, 2, okay? So our toolkit function is f of x is equal to the cube root of x, right? That's our toolkit function that we're working with, and it looks like this one has been shifted somehow. So let's see, our y prime is equal to a, some scaling factor, times the cube root of x prime. And so what I need to know is, what is this scaling factor right here? What is that number right there, okay? So to figure out that number, I'm going to take this ordered pair. So that's in x prime, y prime, that's the ordered pair 1, 2. So let's plug that in. Let's plug in that ordered pair. So that tells me 2 is equal to a times the cube root of 1, which says that 2 is equal to a, because cube root of 1 is 1, 1 times a is a, right? Nice. All right, so that tells me that what I know so far about my pal g of x here is that the scaling factor is equal to 2. And I know it is a cube root function. And so now let's talk about what was the shift. Well, it looks like it got shifted 1 unit to the right. So that's x plus 1. It looks like it got shifted 1 unit down, so that's a minus 1. All right, I'm going to leave you to put that in Desmos. I'm going to pick up the pace a little bit here and check and make sure that we got that right, okay? All righty. One last beast here. I think this is the last one we're going to do. Yep, this is it. Okay, last beast. So write an equation for the transformed toolkit function graph below. Okay, so it looks like our stock function was f of x is equal to the square root of x. So my new translated origin in terms of the x prime, y prime is right here. That's my x prime, that's my y prime. Okay, so that tells me that y prime is equal to some scaling factor times the square root of x prime. All right, let's go see if we can read an ordered pair off of this coordinate system. And it looks like negative 2, 2 is an ordered pair in x prime, y prime. In other words, I shifted it to the left 2, went up 2, okay? So if that's the case, let's go ahead and plug that in. Oh, wait, time out. This is not my right y prime here, is it? Look, oh, yeah, because the stalker goes like that, doesn't it? Oh my gosh, this has been reflected, hasn't it? This has been reflected across the y-axis. So I need to put a negative in here, don't I? Right? Because look, remember, if I had an x and I made it a negative x, that means I reflected it across the y-axis, right? All right, cool beans. Now, and only now, because it would have been a big trouble. I would have been in complex numbers if I hadn't noticed that up front, right? So that tells me that 2 is equal to a times the opposite of negative 2, which says that 2 is equal to a times the square root of 2, right? Okay, that tells me that 2 over the square root of 2 is equal to a. So that's my scaling factor. Now the funny things about square roots is that they can come in all sorts of different flavors. So if we multiply this numerator and denominator by square root of 2, in other words, multiply it by 1 in that form, square root of 2 times square root of 2 is square root of 4. Square root of 4 is 2. 2 divided by 2 is 1. So that gives me that the square root of 2 is my scaling factor a. Make sure what I just did there makes sense to you, okay? All right, so let's get ourselves a little more room here. Running out of space, but not too badly. Okay, so what do we know? We know nothing. No, we know is we've got a scaling factor now. We know that g of x has got this scaling factor of the square root of 2 out in front of it. We know that it is the square root and that it's going to have a negative on it, right? But we also now know that we've been shifted somehow, okay? So we've got to be careful. Which way do we get shifted? Well, we got shifted 3 units to the right. So it's the opposite, put in the negative, and now with parentheses, you're going to put in the x minus 3. In other words, you substitute in the shift, the left to right shift, by using parentheses. If you don't do that, you're going to end up possibly not having the correct IGN on the number you're looking for. So another way we could write this is the square root of 2, distributing that negative, would be negative x plus 3, okay? Now, a little trick. Square root of 2, if I square both sides of this, I get back what? 2 is equal to a squared, right? Well, taking the square root of a would get me back, if I think it, like assisting that a is a positive number, it would get me back 2. So, we'll bring it along here. I'll just forget what I was talking about over here. I'm just making this way more complicated than I need to. These two are being multiplied together, so root 2 comes inside, and if the root 2 came inside, it would be 2 times negative x plus 3. What I'm saying is that, look, recall that if you have the square root of a times the square root of b, then that's the square root of a times b, all right? So that means I can bring the 2 inside of there, which says this is the same thing as saying this is the square root of negative 2x plus 6. So if you graph this bad boy right here and you graph this bad boy right here, you're going to see that they land right on top of each other. Okay. Oh my gosh, that was a lot. It's a huge amount of material that we just did real quick here. Again, as I opened up with part 1 of this, strongly encourage that you read the book and watch the videos. They aren't necessarily going to use this X prime, Y prime idea that I'm using. You're welcome to stick with that if that makes sense, or if you like the way the book's videos do it differently, then please stay with whatever makes sense to you. Also, Khan Academy's got some good videos on here also, so make sure you do whatever it takes for this to make sense to you. Particularly you folks who are taking trigonometry now or in the near future, you're going to find understanding this stuff now is going to make trig a lot easier for you. Okay, thanks a lot for your attention. I appreciate you doing it. Get after the homework. It's due next week.